Thank you, and welcome to FloTHERM XT, compressing the thermal design process. Specific topics we will discuss include an introduction to FloTHERM XT, an overview of the electronics thermal design process with a traditional general purpose simulation product, and the thermal design process with FloTHERM XT. We will look at examples of working with MCAD data, and also examples of working with ECAD data. We'll then finish up with a brief FloTHERM XT demonstration based on the BeagleBone Black, an open source single board computer released in 2013. So let me introduce FloTHERM XT to you. In one sentence, it's a specialized electronics cooling product line supporting design processes from concept to verification. Its primary and industry unique aspect is its ability to support thermal design requirements from concept through detailed implementation and onto final design verification, while retaining data model consistency and cleanly supporting data evolution as other mechanical or board layout changes are introduced in the process. FloTHERM XT is a unique software solution that delivers on interconnecting both the MDA and EDA design flows, as we'll see in this presentation. The software is CAD-centric in design and operation, but has a configurable UI that supports the needs of design engineers and thermal specialists who may not require access to all the CAD functionality. The product is focused purely on electronics cooling applications and has been built on 25 years plus of innovative technology in FloTHERM and utilizes the general power and sophistication of FloEFD as an enabling technology for meshing and solving. FloTHERM XT is used at the system level, at the board level, and at the IC level. The BGA example, courtesy of Thales, looked at the improvement in predictive accuracy of thermal models when the bond wires were included. To understand the process improvements that FloTHERM XT provides, we need to first look at how traditional CFD integrates with the MDA and EDA design flows. The first step is usually to create some geometry within the CFD tool, and then assemble the model by taking other data from these design flows, particularly in late design. Native CAD geometry first has to be simplified before it can be exported for use by the CFD tool, as you will see in a moment. It is exported in some neutral file format like STEP, and then it has to be cleaned, meaning that the problems of small gaps in the geometry have to be closed before it can be used for analysis. Similarly, native EDA data has to be exported, for example as an IDF file. Components that are not important to the thermal design are usually filtered out to simplify the assembly. As EDA tools usually work in 2D, information about the layer stack-up for the PCB has to be provided, and thermal models provided for the components that need to be considered in the simulation. The next step is meshing. Traditional CFD meshes the surface first, and then the flow space, and is error-prone as features of the geometry can cause the meshing algorithm to fail, necessitating more work to clean the geometry. And if that fails, the CAD geometry must be simplified further, re-exported, and the cleaning step repeated before meshing can be reattempted. Meshing can also fail because of the geometry imported from the EDA system. In this case, there is little option but to re-export the native EDA after making some modifications in the EDA system and repeat the geometry preparation steps. Failures associated with both the MDA and EDA geometry can make meshing a lengthy and manually intensive process. Once complete, boundary conditions need to be prescribed to complete the definition of the thermal model. For example, the powers that the components consume that becomes heat. It is then possible to solve the case. However, failures can occur if the mesh quality is poor, as skewed cells and large size differences can cause the solver to converge slowly, or worse, diverge, and if successful, can result in a poor quality result, with the simulation giving erroneous results. Post-processing is needed to interpret the results, and finally some form of report generation is needed to feed recommendations from the simulation back to the design teams to improve the design. The consequence of this is that it can take a long time to go through the cycle, by which time the simulation model has become stale as design has moved on, making implementation of any design recommendations problematic. Let's now look at the thermal design process with FloTHERM XT. The create geometry step is as before. However, the geometry can be CAD geometry, created within FloTHERM XT or smart part based. The assemble model step is compressed because FloTHERM XT can directly work with CAD geometry, so CAD can be exported in the CAD system's own native format and used directly in FloTHERM XT. If required, unnecessary detail can be removed by rewinding features of the model within the CAD system. Similarly, native EDA data can be exported. All the processing steps are incorporated into a new module, FloEDA Bridge, which simplifies the preparation of the model. Component powers are also specified via FloEDA Bridge, which then allows a fully defined thermal model to be read directly into FloTHERM XT. Meshing is compressed as we avoid all the problems with the traditional CFD approach to meshing by using object-based mesh controls and a smart cell mesh technology that does not suffer from mesh quality problems associated with body-fitted meshes. So the solution process also proceeds quickly and without convergence problems. Report generation is automated so that recommendations from the simulation can be fed back to the design team in a very short elapsed time. Also, previous settings are retained by FloEDA Bridge, so EDA design updates can be re-imported and any previous simplifications to the MDA geometry can be repeated before the geometry is re-imported into FloTHERM XT. So the simulation model can keep pace with the changes in both the MDA and EDA design flows, hence the subsequent simulations can be undertaken even faster. An efficient electronics thermal design process involves leveraging existing MCAD and ECAD data in a repeatable and scalable manner. FloTHERM XT offers a wide range of supported file formats, including native FloTHERM files. This allows use of existing models from past designs or from a supplier. A unique feature of FloTHERM XT is how easily a CAD-based model can be transformed into a FloTHERM XT thermal model. To illustrate this concept, I've downloaded a CAD model of a DIM from GrabCAD, courtesy of E. Washbrook. I have the CAD model loaded into FloTHERM XT. I'd like to create a FloTHERM XT library part that I can use in other models. I will use the PCB Smart part to assign the material properties of the PCB, and the Network Assembly Smart part to create two resistor components. Since the components are patterned, I will only need to assign the properties to one component. I will also apply mesh settings so that the DIM will be meshed at appropriate resolution independent of the model it is used in. I'll begin by assigning a minimum feature size of 1 mm, which controls the mesh resolution for this assembly. I also assign a material of typical connector to the assembly. Next, I will use the PCB Smart part to assign a 20% copper coverage to the PCB extrusion. The last step is to create the two resistor model. I can specify capacitances as well, but will only assign a junction to top and junction to bottom resistance in this example. I select the surfaces that represent the top and bottom of the component. I can now drag and drop this assembly into my library for use in any model. Electronic systems invariably involve a printed circuit board or PCB, or simply a board. The thermal model of the PCB may need to be manually created in the thermal design environment or imported via the IDF format, or a more detailed format such as ODB++ or Mentor Expedition. FloTHERM XT supports the EDA workflow through the FloEDA Bridge. Let's take a look at these workflows, beginning with the Creating a PCB example. I've opened FloEDA Bridge and the default outline is displayed. I'll open the outline editor to show how more detailed board outlines can be created interactively. The shape is controlled by specifying the arc angle between vertices. You can create a new vertice either through the properties sheet or by clicking and dragging a vertice to create a new one. Next, let's add a few components to show how they can be positioned and changed. I'll change these components to two resistor models and specify the power. Lastly, I'll add the obligatory angle component. The size and angle of the component can be controlled through the property sheet or by dragging the handles. The next example is based on an IDF file import. The first step will be to replace the current board outline with that defined by the IDF file, as well as the component layout. We have the opportunity to specify the number of layers as it isn't defined in the IDF files. We see that the components are modeled as simple or a simple extrusion with no power. To assign powers, I import a power list. A power list is a comma delimited file containing reference designators and powers. This is a quick and efficient way to assign many component powers. Next, I want to replace any parts on the board with thermal models for my library. These can be detailed or compact thermal models. We see that the power remains unchanged, but the model is now a 2-resistor compact thermal model. The last step is to filter out any components that aren't relevant for the analysis. We can filter parameters such as size or power or a reference designated letter, R for instance. We are now ready to transfer the board. The last example we will look at is based on the ODB++ format. This format includes geometric information of the nets. In this context, a net is the copper traces and vias that carry a specific electrical signal or current, but may also have a significant effect on the heat transfer. Historically, it has been time-consuming and challenging to build a thermal model with this much detail. With FloTHERM XT, we will see that it is a process that doesn't require advanced CAD skills. I've loaded the ODB++ file of the BeagleBone blackboard into FloEDA Bridge. We see that the stack up as well as the copper traces have been imported. I'll pick a net to model explicitly as an example. Next, we'll import the power list. Let's transfer the board into FloTHERM XT and look at the explicit trace. I'll isolate on the trace and zoom in so we can get a better look. Let's now take a look at a brief demonstration from start to finish of the BeagleBone Black project. I'm going to start with a series of still images that show how to set up a new project, and then we will move into the software. I have the CAD model of the enclosure loaded into FloTHERM XT. To create the project, we will start with the new project wizard. Since I have an active assembly, I will use it as the top level project. Next, I choose the unit system I'd like to use. I set my preferred units as the current units. I can now identify key parameters of the analysis, such as the domain and solution type. In this example, I will change the gravity to be in the -z direction. I will also change the domain size, as this is both an internal and external analysis. Lastly, since this is natural convection, I want to include thermal radiation. I'll leave the default fluid as air and set the default solid to nylon 66. The last step of the wizard is to review my settings and finish. I now have a FloTHERM XT project. The solution domain is displayed as the rectangular border around the enclosure. There are only a few more steps before you're ready to solve the project, including importing the PCB. Before I import the board, I want to specify the bottom of the solution domain as symmetric to represent a tabletop that I haven't modeled explicitly. Though I set the domain size and location in the wizard, it can be easily set in the property sheet. I launch FloEDA Bridge and import the ODB++ file. I'm going to set the modeling level to detailed, which will model each layer of the board discretely. I then import the power list. The next step is to swap in library parts. I'm swapping in a combination of detailed components and compact thermal models. The last step is to filter out the smaller components and transfer the board to FloTHERM XT. I'll hide the solution domain. I'd like to add a heatsink to the processor from my library. I need to mate the heatsink to the component so that it remains centered on the top of the component. I'm now ready to generate the mesh. We see that the meshing process took about 1.5 minutes with a little over 190,000 mesh cells. Let's take a look at the grid in the heatsink area. As part of the heatsink library definition, I have specified the grid resolution to maintain, as well as the material and thermal interface material. We're now ready to solve the project. It took a little over an hour to solve on my laptop. Let's take a look at some of the hotter components. Now let's take a look at a contour plot of temperature. We'll also use the plot probe to interrogate the temperatures. You can view the plot with or without the mesh, so I'll turn off the mesh also. There are a number of plots that can be created, but I'll create a surface temperature plot to use in a report. I want a top view with the heatsink shown as wireframe. Let's now generate a report. There are a number of options when creating the report, but I'll generate a full report in a Microsoft Word document. I'll choose to report detailed information for the PCB. The report generation features a valuable method of generating the model output. The table is color-coded. Green indicates the temperatures are significantly under the maximum allowed temperature, as specified in FloEDA Bridge. Even the filtered components report the board temperature in that location. Compact thermal models report the temperatures at the nodes, in this case the junction, case, and board. The report also includes information on the model convergence. Any screenshots taken are also included. Parametric studies are easy to consider in FloTHERM XT. In this demonstration, I'll modify the height of the heatsink fins, though multiple parameters may be considered simultaneously. I'll set the heatsink fin height to 4 millimeters and 6 millimeters. I'll set the output parameter to the junction temperature of the processor. I won't solve these, but I did want to show you how the Scenario tab allows you to click on a scenario. If there were results displayed, the results would update for that scenario. FloTHERM XT is a simulation product specifically designed to accelerate the thermal design of electronics products. Key features that enable this gain in productivity are a CAD-centric approach that allows for direct access to the CAD geometry in the thermal model, a flexible and robust connection to the EDA workflow via the FloEDA bridge, smart part technology that allows for quicker and more sophisticated model creation, and smart cells, an easy-to-use object-based meshing technology that is ideally suited for the thermal design of electronics.